Hello everyone and welcome to the presentation of NATSA, a near data processing accelerator for time series analysis. I'm Ivan, a third-year PhD student at the University of Malaga, Spain, and this work has been done in collaboration with people from Safari Group at ETH. Here is the executive summary of my talk. The problem is that time series analysis is bottlenecked by data movement in conventional hardware platforms. The goal of this work is to enable high-performance and energy-efficient time series analysis for a wide range of applications. As contribution, we propose the first near data processing accelerator for time series analysis based on matrix profile algorithm. NATSA provides up to 14.2 times higher performance and consumes up to 27.2 times less energy than a DDR4 platform with 8 out-of-order cores. NATSA outperforms an HBM NDP platform with 64 in-order cores by 6.3 times while consuming 10.2 times less energy. Here you can see the outline of the talk. First, I will motivate the acceleration of time series analysis. Second, I will present NATSA design. Third, I will present NATSA evaluation. And finally, I will present some conclusions. Let's start with the motivation. Time series analysis has many applications, like climate change, medicine, economics, signal processing, even astronomy, and many more. Two of the most used primitives for time series analysis are Motifs and Discords. Given a sliced time series into subsequences, Motif discovery focuses on finding similarities, while Discord discovery focuses on finding anomalies. Here you can see a naive example of anomaly detection. We have a very regular time series which has a very different subsequence over here. If we use the Euclidean distance to measure how similar are the subsequences within this time series, we find that for the most different subsequences, we obtain higher distance values. Matrix Profile is an algorithm and an open source tool intended for Motif and Discord discovery. It is very easy to use, only the subsequence length is needed, and it is exact and an anytime algorithm. Here you can see how the algorithm works from a high-level perspective. We have a distance matrix and the profile, which is the output of the algorithm. Each cell of the distance matrix contains the distance in terms of similarity between two given subsequences of the time series. Matrix profile uses the Euclidean distance as a metric. What we actually obtain is the profile. The profile contains the minimum values for each row of the distance matrix. In other words, what we obtain is the most similar subsequence for a given one with respect to the whole time series. We also store the index of that subsequence. If you want to know more details about the algorithm, please take a look to the paper. SCRIMP is the state-of-the-art CPU matrix profile implementation, but there are also GPU and heterogeneous CPU-GPU versions available. We characterize SCRIMP using an Intel Xeon Phi KNL. Here you can see the bandwidth usage and the speedup we obtain when using two different types of memory, HBM and DDR4. We observe that when we change from DDR4 to HBM, we obtain significant performance improvements. And if we use DDR4, the performance doesn't scale beyond 32 threads. We also perform a rough-line analysis of SCRIMP and find that its animatic intensity is very low. So in conclusion, SCRIMP is heavily bottlenecked by data movement. I already showed that time series analysis is very important for a wide range of applications and it is bottlenecked by data movement. So the goal of this work is to enable high performance and energy efficient time series analysis for a wide range of applications by minimizing the overheads of data movement. To this end, we propose NATSA, the first near data processing accelerator for time series analysis that exploits 3D stacked HBM memories and specialized processing logic. Let's move to NATSA design. NATSA is designed to fully exploit the memory bandwidth of HBM and employ the required amount of computing resources to provide a balanced solution. NATSA consists of multiple processing units, PUs. Each PU includes energy-efficient floating point units and bitwise operators. PUs are designed to compute batches of the diagonal of the distance matrix following a vectorized approach. NATSA is integrated in the same silicon interposer with an HBM memory, as you can see here. NATSA PUs consist of 4 hardware components. First, we have the dot product unit. Second, we have the distance compute unit. Third, we have the dot product update unit. And finally, we have the profile update unit. The execution flow through the hardware components of a PU includes the following steps. First, the dot product computation of the first element of the diagonal. Second, the Euclidean distance computation of the first element of the diagonal. Third, the first profile update. Fourth, the dot product update. Fifth, the second and successive Euclidean distance computations. And sixth, second and successive profile updates. We ensure load balancing among PUs using a static partition scheduling. We assign pairs of diagonals to each PU that sum the same number of cells to compute. Here you can see an example for two PUs, PU0 and PU1. What we do is to assign PU0 the third and the 10th diagonal of the distance matrix, and to PU1 the fourth and the 9th diagonal. So both pairs of diagonals have 9 elements, and we continue this scheme until the whole distance matrix is assigned. If you want to know more details about this scheduling scheme, please take a look to the paper. If we randomly order the pool of diagonals that each PU has to compute, we additionally ensure that the anytime property of the algorithm is preserved. And if the user interrupts its execution, a partial valid solution is obtained. We provide the user an interface to invoke NATSA. The user is responsible for allocating the time series and providing the subsequence length. At NATSA, we provide the user the compute profile and profile index vectors as a result. Here you can see the NATSA API with NATSA function. It precalculates the statistics, allocates the private profiles, calculates the diagonal scheduling, starts the accelerator, and performs the final reduction. Let's move to the evaluation. We use an in-house integration of searching and Remulator to simulate the general-purpose hardware platforms. We use MacPath to obtain area and power for the general-purpose hardware platforms. We use the integration of Aladdin and Gen 5 to obtain performance, power and area of NATSA. And finally, we obtain the memory side power consumption using Micron Power Calculator. We define several representative simulated hardware platforms for the evaluation. We have DDR4 out of order with 8 cores, DDR4 in order with 64 cores, HBM out of order with 8 cores, HBM in order with 64 cores, and NATSA with 48 PUs. We also evaluate NATSA against real hardware platforms like Intel Xeon 5KNL, NVIDIA Tesla K50C, and NVIDIA GTX 1050. We first compare the performance of NATSA with respect to the general-purpose hardware platforms. We use time series of different lengths, and we observe that NATSA outperforms the baseline DDR4 out of order by up to 14.2 times, 9.9 times on average. We then compare the power consumption of NATSA with respect to simulated and real hardware platforms. Here you can see the power consumption for each component of the evaluated platforms. As we can observe, NATSA has the lowest power consumption and most of its power is consumed by memory. Next, we compare the energy consumption of NATSA with respect to simulated and real hardware platforms. Here you can see the energy consumption for a given time series. NATSA is the one that requires the less energy to perform the computation. We observe that NATSA reduces energy consumption by up to 27.2 times over DDR4 out of order, by up to 10.2 times over HBM in order, and by up to 1.7 times over an NVIDIA K40C. Finally, we compare the area of NATSA with respect to the simulated and real hardware platforms. We observe that NATSA is the one that requires less area. NATSA, even at 45 nanometer technology node, requires the least area. Finally, let's move to the conclusions. The problem is that time series analysis is bottlenecked by data movement in conventional hardware platforms. The goal of this work is to enable high performance and energy efficient time series analysis for a wide range of applications. As contribution, we propose the first near data processing accelerator for time series analysis based on matrix profile algorithm. NATSA provides up to 14.2 times higher performance and consumes up to 27.2 times less energy than a DDR4 platform with 8 out-of-order cores. NATSA outperforms an HBM NDP platform with 64 in order cost by 6.3 times, while consuming 10.2 times less energy. So that's all from my side. Thanks for your attention, and I'll be happy to answer any question you may have.